Hi, Sugar Plums. We're going to just pick right up where we left off yesterday with L'Hopital. Um, the stuff for today is how we're going to tackle all of these exponential indeterminate forms. So if you remember, I think I'll just write all of them again. These are your 7 indeterminate forms. It is imperative, that means important, that you know them and can recognize them. From yesterday, these are the only 2 forms that you can L'Hopital. From yesterday, this one is easy. You force it into, not easy, but this one is quick to turn into a L'Hopital. You're going to force it into a quotient by throwing one of those underneath. From yesterday, this one's quick to force as well because you can do a common denominator to force it into a quotient. And then there's these 3, and this is where we're going to lovingly spend our time today. So you handle all 3 of them the same way. So I'm not going to work 3 different examples. All exponentials are the same. I'm actually probably just going to work one because it's Friday. Here's an exponential indeterminate form. I choose to use n today because I'm in charge. All right, step 1, plug in, says that this would be a 1 plus 1 over really big raised to the really big. This thing's going to 0, so this is a 1 to the infinity. If you haven't heard me say it yet, I'm saying it now. This indeterminate form hurts me the most. It just hurts so bad. How come 1 times 1 times 1 times 1 times 1 forever doesn't just equal 1? Well, I'm going to show you. Okay, so if you remember back to last week and the week before and the week before when we were taking derivatives and we had these lovely things called hyperexponentials. I hope you remember that name, even if you remember nothing else. Those are functions where your base is a power of x and your exponent is a power of x. And to work around that, we force them to be base e instead, because base e we understand. But the only way you can do that is if you throw a natural log. But that lets you do all those really strange log rules like Birdie. And this was the function we actually ended up working with to take a derivative. We're going to do the same thing for our limit. Okay, so this was just hopefully a quick reminder for you. We're going to do the same thing for our limit. So I don't like base 1 plus 1 over n. I choose to use base e. So I'm going to use base e. So if I e it, I'm going to throw my limit up here because it doesn't matter. Like n is the thing moving in the limit, and all of my n's are up in the exponent. So I'm just going to keep them close. Then you need a natural log to keep it true. 1 plus 1 over n raised to the n. What that allows us to do is birdie all the way over that n and turn this into e to the lim big n times natural log of 1 plus 1 over. Okay, all we've done is a rewrite. But where we've taken ourselves is now this limit, if I plug in, I have infinity times. This would be the natural log of 1, which is 0. So what you've done is you've taken this 1 over infinity indeterminate and turned it into a 0 times infinity indeterminate, which is fine. It's still indeterminate. But the problem is it's also still not a L'Hopital indeterminate. So the way we handle product indeterminate is we force it to be a quotient. I choose to move this term underneath because that would be too messy, and I don't feel like messy. But what I am going to do while I'm here is I think I'm going to write these things together. So this would be an n plus 1 over n. That might help me later. I'm not sure. Let's see where the algebra takes us. I like to make my base e super giant because sometimes you forget it's there. So this is going to be the natural log of n plus 1 over n over 1 over n. All right. Again, I still haven't done anything, just rewriting. But we have now rewritten this in such a way that it's now a 0 over 0. So here we go. Because it's now a 0 over 0, we can L'Hopital. Base E, making huge. I like that my paper continues forever. Let's see. The way you take, wait, I need a limit. The way you differentiate a natural log is you reciprocate the input. So I'm not going to do 1 over. I'm just going to reciprocate it. But then you have to take the derivative of the inside, and that's going to take a quotient rule. So low, d high is 1, minus high, d low is 1, all over low, low. Man, I hope that cleans up. And then down here, this is an n to the negative 1. So it's a negative n to the negative 2. I'm going to write it that way. I know it just looks bad, but it's going to be fine. It's going to be fine. This is n minus 1. So n minus n is gone. And now I have a negative 1 times n. So this is like a negative out here. Oh, but a negative over a negative makes a positive. See how quickly things are disappearing. I have an n squared and an n squared, so those are gone too. And I'm finished. Like, maybe that was too fast algebra. So let me show you. So what did I get when I cleaned that up? That was just a negative 1 times a negative 1 over n squared. If I flip this bad boy down here, it's an n squared over 1. That's how I was able to do that so quickly. I lost my negative. And the negative and a negative makes a positive. So there, that's what I'm left with. There's no more natural log. I know and you know this is still an infinity over infinity if I take the limit as n goes to infinity. But do you remember all those super fun, super fast shortcuts? If you have the same degree on top and bottom, this is a degree of 1, this is a degree of 1, then we get to look at just the leading coefficient. And so our leading coefficient is 1 over 1. If you don't remember those, it doesn't matter. L'Hopital again. And this is a quick L'Hopital because it's just derivative of the top, which would be 1, derivative of the bottom would be 1, and you're finished. So if you don't remember those shortcuts, you can still make it through. But there's our answer, e to the first. Oh, goodness. Hold on. Let me zoom out of this mess. Are you telling me that the limit of 1 plus 1 over n to the n as n goes on forever is e? That's wild. This is a 1 to the infinity that we just proved equals e. So sometimes 1 times 1 times 1 times 1 equals 2.7. E is a really important number in calculus. Like pi was a really important number back in geometry. E is really important to us in calculus. This is a limit definition of E. This is well known, well established. Everybody who's anybody knows that the limit as n goes to infinity of 1 plus 1 over n to the n equals E. I'm going to tell you where it came from, but I need to put all of my hearts and stars and rainbows and horseshoes and blue moons because it's very important that you have this in your memory. It's going to be super important in like January, which feels like a long ways away, because it is, but it's really important to me that you can recognize the limit definition of E. And there's actually 2 of them, but if you know one, you can know the other, because the other is what if you reciprocate your infinities and go to 0 instead. So I'm going to use an H instead of an N just so you don't confuse yourself, but maybe that's more confusing. So if I let n go to infinity, 1 over infinity is a 0, right? So if I need to make a 0 now that I'm going to 0, it's just, I made it an H, and this would be 1 over H. So these are 2 limit definitions of E. This guy is the one you're going to see more in January, but they could both pop up. If you recognize them, then all of this work we did up here doesn't have to be done. You just write E and move on. And then the variations on, so let me just write one real fast, and then I'm going to tell you where E came from. We're going to take a little history lesson. So if you have a coefficient and a coefficient, those would end up being your powers on E. So if somebody asks you to go take the limit as n goes to infinity of 1 plus 6 over n to the 1/2 n, you would say E cubed, and you would just write down E cubed and show no work and then move on with your life. Okay, let me tell you where E came from. E came from one of the Bernoulli brothers, and I don't remember which one because they're all the same, but they were sitting around trying to talk about money because that's what you would talk about back in those days. And they were like, hey, what if you had $1 and you compounded it one time a year at a rate of 2? So like, remember back when you did exponentials? So compounding twice a year, that would give you $2.25 at the end of the year. What if you had $1 and you did it 3 times a year at 33%? That would give you $2.37. What if you had $1 and you did it 4 times at a quarter? You'd get $2.44. And then, because they had so much time on their hands, what if we did it forever, compounding continuously? And then they found this number, 2.71828. That's not true. They didn't find the number. They just found that it equaled E. The reason it's called E is because it was discovered by this lovely man named Euler, who we're going to spend a lot of time with in end of February-ish. But that's where E comes from. Little history lesson for you. Maybe I'll make a bonus question on your test next week that just asks you to tell me a fact about E, and we'll see what you come up with. Don't tell your friends because they're not still watching this video. Okay, let me know if you need anything.